So just quick introduction who we are. I'm from McLaren Applied. First part of that name quite well known, second half not at all. We were part of the McLaren group, so automotive making the supercars and racing, doing all of the Formula One IndyCar, until a few years ago where we were spun out, privately acquired by Greybook Capital. We've been an entity in our own right for about 30 years, always focused as a tier one developing kind of future-focused products, a lot of control-based, but then recently a lot more electrification. So within McLaren Applied, we're split into 3 business units, and I'm from automotive, where our focus has been on power electronics. So if I just take you through... our journey to date on the power electronics side. We've obviously come from a kind of relatively niche background with the motorsport play, the high performance automotive, and we've been working on power electronics for about 5 generations, 10 years. But the problem was, it was always customer funded, specific kind of product development only for them, very kind of niche and limited given the size of our company as well. And we've always tried to push the boundaries of power electronics, and we were the first people to use silicon carbide in Formula One within the inverters, but really kind of always struggled to make that transition through. And a few years back, we wanted to change our strategy and structure and be more of a product-driven business rather than just responding to customer demand, but we needed support with that. And the key kind of enabler for that was a government-funded APC project as part of a consortium that focused not just on the inverter, but building out the entire power electronics supply chain. So that project was called ESCAPE, end-to-end supply chain development for automotive power electronics. And there were about 12 partners in this consortium, about a £20 million project. So it was quite ambitious for the scale, and it was really looking at everything from the epi layer growth all the way through to the end tier one products, and how then we could take them to market, really kind of capitalize that with different applications. And I think one of the things that was key was that this was supported and also driven by partners that weren't just doing the technical development, but were doing the engagement with the OEMs or the market analysis to constantly steer the innovation at the source and drive it through to make sure that the products that were developed at the end by the tier ones was something compelling, had a good product market fit. So just to cover what were the objectives and the scope of that project, really it was to do the end-to-end and to try and apply innovation to put the UK in a space where we could be on the front foot, really. So that was anything from using kind of the catapult centres to help pioneer innovation, do new kind of daring, low TRL kind of investigative research, all the way through to getting that aligned through the supply chain. And like I said, ultimately coming up with tier one level products that were aligned to OEM demand through different markets. So as I said, we kind of constructed the consortium so that we had a partner for each kind of level within the supply chain growth, starting from the wafer itself and then the epi layer, all the way through to then the SiC device fabrication. And you'll see on the later slides, it was really focused on how can we push the new frontier. So this was for us focused on trench MOSFETs with the silicon carbide on a 6-inch wafer. And then taking that through to looking at the packaging, how we could best optimize those devices, and then really build the products on top. So the whole idea was if we can work closely together, we can help best optimize the end products through so that they're as compelling as possible when they go to market. So some of the technical objectives then, with Vishay and Classic, like I said, this was really focusing on moving from kind of planar MOSFETs to trench dies, so benefiting there from a higher kind of technology perspective, more die per area, getting your cost and efficiency kind of improvements through the production scale, really at the cutting edge of what was available kind of in market. Then looking at the advanced packaging solutions, again, a consortium attacking the problem from different angles, not just looking at the efficiency of the package itself, but how then, when you look forward to the end solution, how you can do some novel kind of thermal integration to, again, look at that system benefit and how holistically, when collaborating, you get kind of the most impact. Then we'll cover kind of what each of the three tier ones did. So ourselves as McLaren Applied, we were focused on the traction inverter, primarily for automotive. Then Lyra developed a kind of platform of DC-DC converters. One of the nice things was, even within the scope of the project, they were able to deliver multiple product variants, kind of proving out the feasibility of that being able to scale. And then we also had Turbo Power Systems, who were looking at EV charging as well. So what you see here is each of the different kind of work packages, and I'm not going to try and dive deep into any of the detail, but I think the important thing to take away is how we've intrinsically tried to link each of these. And you'll see some of the partners are common across the different work packages, again, owing to that point around if we focus on the collaborative element, we'll be able to achieve things that we wouldn't in isolation, and also then position ourselves really strongly against the competition. And again, we've kind of got work packages 1 through to 5, 7, and 6 on the right-hand side. They're very much focused on the product development. But the other kind of supportive work packages on the kind of left bottom-hand corner around the market analysis, the dissemination and OEM engagement, really helped make sure that what we were developing was tightly kind of controlled and ultimately going to have a really good product market fit. So just to go into those in a little bit more detail, how that then constructed, what were the kind of key outcomes from each of these work packages. The first one I've kind of mentioned, from that epi-layer growth from the 6-inch 1200 volt silicon carbide, kind of optimized for trench dies. That then went into the classic fab and the work with Vishay and Warwick Uni, looking at how they can optimize then the fabrication on top of those wafers for these really cutting-edge kind of trench MOSFETs. Then on the right-hand side, it was how can we take that source material and optimize it into a series of different modules, which would then supply the tier ones for each of their different applications. So on the left-hand side, the 80 amp half bridge, that was very much focused on the DC-DC and being able to then scale for the EV charging solutions, whereas the 450 amp three-phase solution was more for the traction inverter for automotive applications. Coming on to the tier ones, like I mentioned, Lyra Electronics developed a DC-DC kind of platform that was pretty much a plug-and-play solution that was scalable. So within the project, they developed both a 25 kilowatt and a 100 kilowatt solution using nominally all of the same kind of base layer componentry as subsystems and the modules from the last slide, just showing the kind of flexibility that was there inherent in the design. And they're now taking that to market. I will go on to the inverter in a little bit more detail on the coming slides, but our kind of ambition and scope was to really develop a silicon carbide optimized inverter and try and maximize the benefits that silicon carbide gives you in terms of efficiency, package density, those kind of things. And then finally, Turbo Power Systems, they've been developing, again, a kind of modular array of charging solutions. So anything from kind of 400 volt up to 11 kilovolts in their applications. Again, picking up the modules from the other work packages and being able to deliver multiple different products to market off of the back of that. As well as just the product side of things that were developed and how they can then be exploited, I think one of the things that's really important to note is some of the investment that was then driven off the back of the successes and the collaboration within the project. So there were 2 acquisitions by Vishay from partners within the project, pretty much driven off of the work that we did together. So the first was Max Power, who were developing kind of both planar and trench MOSFETs, and Vishay acquired those. And then after that, Vishay also acquired Newport Wafer Fab. and since then have continued to pour more money in. So I think the total investment number is about $410 million, which is a huge kind of success story of the project, the value that external kind of partners see in what's been driven. And clearly alongside this goes a huge amount of job growth, more products come off the back of it, and just, like we said, building out the supply chain, which is exactly what this project was set out to do. Another kind of tangible thing that we tried to pull out of the assessment of the project in terms of successes was then looking at, well, based on the product sales from each of the tier ones involved and the applications that they go into, can we try and convert that to a CO2 type impact? Again, very much with an automotive focus, but based on the kind of sales projections from each of the tier ones, it delivers several million tons of CO2 improvement through the efficiencies that the technology kind of delivers. So again, this is a really nice kind of tangible success story from the project. So the inverter, I will come on to in a little bit more detail because I'm better placed to speak about that, or at least I should be. Like I said, one of our key barriers to entry was we'd come up with 4 different generations of inverter in the past, and we had used silicon carbide, but really there was always that kind of barrier to entry to standard product and going out to the wider market. And being able to collaborate with that consortium of partners and having the government funding alongside kind of de-risked the project enough for us to be able to support that, grow a team of up to 50 engineers, then working on that over a number of years. And this product is now almost ready to go to market. So the SOP for this will be in January next year. And the intention, like I say, was to kind of leverage the benefits of silicon carbide from the outset. And for us, what that meant were a couple of things. Firstly, efficiency. And with peak efficiencies of 99%, we kind of hit our targets. But then also trying to capitalize on the fact that with less heat rejection and faster switching, what you can do is downsize the entire system around it. So we were really pushing the power density perspective. And I'm happy to say that we kind of achieved that. So we got 540 amps RMS peak out of this, which roughly then equates to about 400 kilowatt from a motor that it can drive. And that's in a package of 5.5 kilos and less than 4 litres. So that puts it as market leading in terms of power density. It also opens up a whole world around software and fine motor control, which aligns with our motorsport background as well. But this is to say that kind of the product for us has delivered on the targets that we set ourselves. Outside of the consortium, I guess that was an enabler for leveraging an even wider UK supply chain base. So in some of those cases, we've got kind of dedicated UK companies, like the NCAB group. We use Kestrel for our PCBs. But then also outside of that, we've got, yes, multinational conglomerates, but all the UK subsidiaries that we're working with, so the likes of ST Micro, Arrow, etc. So it's broadened just beyond what was in the consortium, and I know that's true for all of the other partners as well. So exploitation, I guess it kind of, all of that technology development doesn't really matter if it doesn't end up going anywhere. So just a couple of quick slides. Like I said, we are pre-production, so most of our pipeline can't really talk about. But the first one that we can is an exciting project. It's an automotive hypercar manufacturer in the US called Zynga, who are making a vehicle called the 21C, which is one of those ridiculous, I must beat all records type vehicle, which has like 1,000 horsepower combustion engine to start with, and then 3 of our inverters on top powering 250 kilowatt motors. So it's a bit of a beast. That is clearly low volume, high price. But that's kind of like a halo project to start us off. They're actually going into production next month, so ahead of our SOP, which has been a challenge, but also a blessing to kind of prove out the technology on road, drive the limits of performance actually in a vehicle application as well. So that's the first one, kind of the halo program. And then off the back of that, we've got a number more. So one is a UK automotive hypercar. Make of that what you will, there's not many of those. But beyond that, we've also tried to start exploring alternative markets. So APC is an automotive kind of prioritised government structure and funding pool, but the technology that's been developed is absolutely relevant to a number of industries as well. And what we've seen is that automotive has kind of led the way, but over the last couple of years, we're increasingly getting interest from the likes of aviation. So whether that be the eVTOL, which is clearly a huge step and a multi-year kind of development program because none of the legislation is there to support it, through to kind of hybrid applications where they're taking existing kind of airframes, existing powertrains, and then just hybridizing them for mostly takeoff and landing to reduce emissions, increase payload, that kind of thing. So we're starting to see that come through already. We've got a couple of those projects in flight. And also marine, that we're seeing that start to come through as well. So smaller boat applications, typically kind of going on to private customers or small fleet operators. But I think this is just to say that this isn't true just for the inverter, but there's lots of applications and industries coming off the back of the work that was done. Collaboration, again, just trying to hammer the point home. Outside of this project, it's been an enabler for us to kind of build on the strengths of what's been achieved and take that kind of forward for more investment. So once we've got the initial support that gives us some traction, we can take that forward and invest further ourselves, whether that be with other partners to create wider products. So the big thing in automotive is going forward, increased levels of integration. They want the motor, inverter, and transmission all together. And we've started kind of working on that. You can see an example in the top right. Or kind of more novel solutions where you have the motor in the wheel and you have one per corner. And we've got a partner working on that as well. But beyond that, we've kind of tried to take the all the platform learning from IPG5 and develop new product variant. So again, all about building on the foundation set to continue pushing that forward. And we've got a program called 5X, which effectively is looking at taking all of the technology, similar to how Lyra have approached it and Turbo Power Systems. What can we make modular and scalable within that? So we've fundamentally carried over the internals here and focused on flexibility so that it can be tightly integrated into different motors and transmissions, bless you. And again, that just gives us the different kind of options around collaborating with other people to create end solutions. I also wanted to talk about then a follow-up consortium project that came after Escape. So you see the Escape partners on the top half of that screen. We've got a smaller one focused not just on once we've built the supply chain, but then how do we industrialize it and capitalize on all of the technology that's been developed and bring it to higher volume applications. So through the relationships built, with Microchip, for example, we've then formed a new kind of consortium project called SIGNS, so Supply Chain Innovation Engineering for Net Zero, which is focused on automation. So the actual then manufacturing process, once we've got these technologies, how do we compete globally with a kind of cost-effective solution? And for us, this is the process of pursuing automation and looking to reduce our build times and costs that way. So that's been a really good example of how we can not just do a one and done, but genuinely try to form relationships with the partners in the consortium, build off the back of that, and then go on to do more investment, more development, more projects. That is all I wanted to talk through today. Hopefully it's given you a bit of a flavour for how we've approached things, some of the things that can be achieved when you kind of work together. Would definitely encourage anyone in this room to reach out to your relevant quangos for funding, support, and setting up collaborative routes forward. Thank you.